Hi, I'm David Rolnick, and this is an introduction to autoencoders. Let's start out by looking at a picture. What is this? How would you describe it? There are a couple of ways. First, you could say, well, pixel 1 is 98 in red, 103 in green, 120 in blue. Those are the RGB values. Pixel 2, by contrast, is 99, 103, and 125. Pixel 3 is this, and so on. That's one way to do it. Another approach to describe the picture is to say, it's a puppy. It's brown, it's cute, it's sitting on some grass, and so on. Which do you prefer? I know I prefer the second one. And one of the reasons why I prefer the second one is because as soon as I know that it's a puppy, I have an image in my mind. And then that image gets refined when I hear each additional word. So brown puppy makes the image even clearer for me. Brown puppy sitting on grass is even clearer. Within a few words, I have a very clear image in my mind. Whereas with the first approach, I don't have any image in my mind. Even if I were able to keep track of all those pixels, I wouldn't have any picture until the end, until I'd gone through basically all of the pixels. So this is an example of a low-dimensional representation, where we could describe the data in a very high-dimensional way, but through picking cleverly a particular small set of descriptors, we can actually have a very effective way of representing our data without going into the high-dimensional representation of all the pixels. In general, low-dimensional representations are ways to represent high-dimensional data with some smaller number of features. Why might one be using them? First, compressing high-dimensional data. Sometimes it's hard to store high-dimensional data. There just isn't enough space. So one wants to store it more efficiently by throwing out some of it and storing a lower dimensional set of features. Also, it might be useful semantically to identify the most important characteristics, things like object type, color, background, etc. We probably care about things like that if we're trying to understand what's in a picture rather than just describe the picture itself by pixel values. More subtly, sometimes the data itself is actually low-dimensional. So for example, if I were trying to describe the position of my body, I wouldn't have to describe the separate positions of every molecule. I could get a decent way there just by giving the joint angles of my body. That would determine a lot of the positioning of each individual part of my body without having to go into more detail. So sometimes there is actually intrinsically low dimensionality in the data. Why would we be interested in this kind of thing as neuroscientists? Well, two reasons. One, because the brain itself has low-dimensional representations. We use low-dimensional representations in how we think. It's clear from the example of the puppy that I do a better job of thinking about a picture in terms of what is in the picture, as measured by a very low-dimensional set of features, rather than the exact pixel values of the picture. And this is in general true for the way that people think. We think in terms of a much lower dimensional set of features than the sensory input that we are processing, or the amount of data that is available to us in the world. We pick out salient things and we think in terms of those things. Quantifying exactly how those low-dimensional representations are created, maintained, and interact with each other can involve computational models. So what we're going to be looking at today is various ways of creating these low-dimensional representations, even though we're going to be looking at them from the computational perspective rather than trying to match up low-dimensional representations with what may be going on in the brain. And it's a completely separate discussion whether one is actually correctly modeling the way that low-dimensional representations are created in the brain in any particular computational system. So that's one reason why one might be interested in creating low-dimensional representations, because they could be models for how we're creating such representations in the brain. The second reason is just because neuroscience has a lot of data, and sometimes one has very high-dimensional data, and one wouldn't want to work with that data in its high-dimensional form, and so one wants to pick out important characteristics or compress it or something else. And that's completely separate from low-dimensional representations that are actually being used by the brain itself. This is just like any other form of data. Sometimes we want to process it. So for the rest of this intro, I'm not really going to focus on applications, but suffice it to say that these are really two very important classes of applications where low-dimensional representations come into play. So what is a way to come up with a low-dimensional representation? You've probably seen some already. Maybe the simplest one is PCA. PCA involves picking out the top eigenvectors of your data matrix. Formally, that's the vectors with the highest eigenvalues. And what that basically just corresponds to is the aspects of the data that vary the most across individual data points. So the picture, you can see what are called eigenfaces. They're eigenvectors, they're principal components, from the space of human faces. And they're somewhat interpretable, they're somewhat natural features, not completely. Maybe if I were picking out ways to describe human faces, I would say things like nose and mouth and ears and so on. But here you can see that some of the eigenfaces pick out more strongly the nose or the hairline or so on. And what it means for these to be principal components is that you can approximate any human face as a linear combination of these eigenfaces. So you could say that a human face is 0.8 times one of these plus 0.1 times another minus 0.3 times a third, for example. Now, there's something a little bit strange there. We often think in terms of features being additive, so some amount of nose, some amount of mouth, and so on. But here we could have negative coefficients. And that's a little bit worrying if we are thinking in terms of sort of interpretable human comprehensible features. So there's a similar approach, which is non-negative matrix factorization, which is like PCA, except that the components have to have positive coefficients. Instead of just working with any possible coefficients, here you have to be adding up positive multiples of all of your basis vectors, or your eigenfaces in this particular example. A third approach is to use independent component analysis, ICA. And here, the idea is that you're trying to separate statistically independent signals. If you have multiple signals that are statistically independent of each other, they can come together to form something that seems like noise. For example, if you're in a crowded restaurant and you're listening to lots of different conversations, then the sum of all the conversations can sound like noise. But each of the individual conversations is actually very, very highly structured and independent statistically from the others. And there are actually ways to pick out these statistically independent signals that are superimposed upon each other. This is, in fact, one model for what is going on in visual cortex with simple cells, picking out statistically independent visual imagery. I'm not going to go into the details of that, but you can look into that if you're interested. Another way to come up with a low-dimensional representation, perhaps with a slightly different flavor, is a compression algorithm, something like gzip, which is used by your computer to create zip files. And the goal here is maybe different from PCA, NMF, and ICA. In gzip, the goal is really just to compress something as much as possible. It's not trying to be a natural decomposition. It's not trying to be interpretable in any way. It's merely trying to squeeze as many bits as possible out of your representation, so it's as low-dimensional as possible. And so you can see that there are sort of different flavors and use cases for different kinds of low-dimensional representation algorithms. Now let's turn to some more sophisticated, perhaps, methods of coming up with low-dimensional representations using deep learning. Autoencoders. And in its basic form, an autoencoder is very simple. It's a neural network with an hourglass shape. It looks a bit like this, and you can dissect it into three components: the encoder, the bottleneck layer, and the decoder. Let's look at the encoder first. That's going to take your input, which remember is going to be high dimensional, and it's going to gradually make it lower dimensional. In the case of a fully connected network, you just have layers of decreasing width. They start out with a very high width, so very high dimensional input, then it gradually gets narrower over time until you get to the bottleneck layer. And the bottleneck layer is your low dimensional representation. Now, once you've gotten it to a low-dimensional representation, the neural network will expand back out and take it back to the high-dimensional representation. Why it does that will be clear in a moment. And this part of the network is called the decoder. This is the expanding back out part of the hourglass. Now, the idea here is that the encoder and the decoder should roughly be inverses of each other. You're going to train this autoencoder so that the decoder inverts the process of compression. It goes backwards from a low-dimensional representation to a high-dimensional representation. And this is the key point in an autoencoder, that the encoder and the decoder are learning a transformation from high-dimensional to low-dimensional space so that it's possible to go backwards. And because it's possible to go backwards from a low-dimensional to a high-dimensional space, when that happens, it's precisely when the low-dimensional representation is capturing the really important parts of your data. So how do you train for this to actually happen? This is a neural network. You can train it using backpropagation, gradient descent. You can train it to minimize a certain loss function, and there are various examples of a loss function that you might use here. One example is the L2 norm of the difference between the input and the output of your decoder. So d of e of x there, it just means you've applied the decoder to the output of the encoder. And so you're trying to make the decoder basically be the inverse of e. So x should be very close to d of e of x. Now, a key point here is that this is self-supervised. Many deep learning algorithms require labels. For example, if you're trying to learn the differences between cats and dogs, distinguish different images. Here, you do not need labels. It's what's called self-supervised. The data itself sort of provides the labels because the output is coming from the input. In fact, the output is basically the same as the input in the case of an autoencoder. So you don't need to label your data to feed it into an autoencoder. You just need to know that the data exists. You could throw in a database of human faces without any other information, and the autoencoder would learn to compress those faces into a low-dimensional representation. Now, how would you actually use an autoencoder in practice? This is how to create one, how to train it. So you have your encoder and your decoder, and you can actually use them separately. This is something that's rather cool about autoencoders, that you can use the encoder divorced from the decoder, and vice versa. If you're using the encoder, what you're doing is you're getting a low-dimensional representation z from your input, your high-dimensional input x. And the goal here is, if you would like to pick out the salient features, or if you would like to store something more efficiently, etc. You could also use the decoder to get full-dimensional data x from some low-dimensional representation z. And this is really interesting. It's sort of like a generative model. If you're thinking about this, for example, in the context of, say, the image with the puppy, I can create an image in my mind of a brown puppy against a background of grass. And that's because I have a decoder as well as an encoder in my mind. The decoder is basically taking the features used to describe an image and creating an example image that is described by those features. So these two things work together, really. I'm able to create a low-dimensional representation, and then I'm able to generate what could have given me that low-dimensional representation. Something that's very interesting here is that I'm actually able to decode things that I've never encoded before. So for example, if I were to be told that there is a puppy, but it's purple, and it's against a background of space, like stars and galaxies. I've never seen a purple puppy in space, but I would be able to imagine it. In fact, I'm imagining it right now. And that's because the decoder that we have in our brains is really powerful. And actually, there are some very nice models of the brain sort of interpolating between the full deep learning approach to autoencoders and a more neuroscientific approach to creating and working with low-dimensional representations that try to get at this whole process of encoder and decoder and try to model what the encoder could be in the brain, what the decoder could be in the brain. Things like the Helmholtz machine, which is trained in a slightly more biologically plausible way using a wake-sleep algorithm where the encoder and decoder are sort of operating separately. And again, the training process there is a little bit more plausible than maybe than backpropagation. I'm not going to go into the details there, but suffice it to say that there is some really rich work looking at encoders and decoders in the brain. Autoencoders are not the perfect model for the brain, but there are some nice analogies here. So now that we've seen the basic kind of autoencoder, how would one actually be using an autoencoder? We've been talking about images. How would one use an autoencoder with an image? We've seen that convolutional neural networks, or ConvNets, are particularly good when using deep learning to work with images. And how would one do an autoencoder in that context? So the encoder is going to be a normal ConvNet, i.e. alternating convolutional and max pooling, typically, max pooling layers. The decoder, though, it's going to go from a lower dimensional representation back to a high dimensional image. And so that's tricky using a normal ConvNet, because a normal ConvNet has all these max pool layers, which are reducing the dimensionality. How do you go backwards from lower dimensional to higher dimensional? Well, the decoder is actually going to alternate convolutional layers with upsampling. So upsampling is sort of the inverse of max pooling in some sense, where instead of downscaling and reducing the dimensionality, you're actually duplicating pixels to create a larger image. And because you're alternating with convolution, you can actually reconstruct a complicated image that resembles your original. So this is how you would go, how you would use ConvNets in an autoencoder, for example, if you're working with image data. Now I'd like to talk about a few sort of variations on autoencoders, the basic model here. First, sparse autoencoders. The key point here is that it's no longer an hourglass shape. You have a neural network that looks a bit like this, where the bottleneck layer is actually not a bottleneck at all. It's wider than the input and output. Now, how does this work? Why is this an autoencoder? We're trying to get a low-dimensional representation. Well, the reason why it works is because the representation is sparse. In the bottleneck layer, it may have a lot of neurons, but only some of the neurons are going to be active at any given time. So an analogy could be if you're trying to describe an image using only a few words, but those words can come from a very large dictionary. So only a few are allowed to be active for any given input, but there are a large number to choose from. Now, how would you actually train such a model? Well, you have your main loss, which is, again, going to be just the reconstruction loss. How far is the output of your decoder from the original input to the encoder, x? So you're trying to minimize that, but you're also trying to minimize you're trying to minimize the activations in the bottleneck layer. And so this is the sparsity loss. It's just the L1 norm of the encoded representation, the bottleneck layer's activation. You can think of this as a form of regularization, if you like, where you're trying to reduce the number of neurons that are active for any given input in the bottleneck layer. And now to train the overall network, what you're going to do is you're going to try to minimize both of these. You're trying to minimize the main loss, which means that you're reconstructing the input as faithfully as possible with the decoder. And then you're minimizing the sparsity loss, which means that your representation, the output of the encoder, is as sparse as possible. Another variation on autoencoders are denoising autoencoders. I think these are really cool. The idea here is that you add noise to the input. Then the encoder is going to encode the noisy version of the input. And the decoder is going to try to reconstruct the original input without any noise. So in some sense, this is a harder task. You have the original images, you've added noise to them, you've encoded the noisy images, and then you're trying to reconstruct not just the original, not just what went into the encoder, you're trying to get rid of the noise as well. So why would you do this? Well, the primary result is that you get a better encoding. It's better in the sense that you focused on important parts of the input rather than any noise that might exist in the input, because you've been taught to discount the effect of that noise. So you're focusing on the really important parts of your image, like the actual features, the semantic features, if you will. The second result is, in addition to getting a better encoding and decoding, you actually also get a denoising algorithm for free here. So in addition to using the encoder and the decoder, which normally in an autoencoder you could use the encoder to create a low-dimensional representation, you could use the decoder to visualize the high-dimensional version of a low-dimensional representation. And then, in addition, for a denoising autoencoder, you actually also have a denoising algorithm, which is just the encoder plus the decoder, which can take a noisy image, throw it into a low-dimensional representation, and then reconstruct it without the noise. So you've got automatically a denoising algorithm as well as the normal features of an autoencoder, which is really cool. Finally, I'd like to talk about variational autoencoders. What's the motivation here? Again, let's suppose that the input is x, our high-dimensional data, and that the low-dimensional representation that we're getting is z. For example, x might be faces, z might be features like eye color, hair length, and so on. And what kind of representation do we want from z? Well, one thing we want is that each feature should be independent. They should be really describing sort of separate things that can vary independently, like eye color and hair length. And second, we would like to scale so that each feature has the same variance. We don't want, for example, all the data points, all the faces, to have the same length hair. Then hair length wouldn't be a meaningful feature. So we'd like to have each feature be relevant to the same degree. For example, you can get these properties by having z be distributed according to a unit Gaussian, where each feature, each coordinate of z is independent, and each is scaled similarly. Each one has the same variance. So this is a goal. It's sort of the motivation for VAEs. How do you actually get that out of an autoencoder model? Well, the intuition here is we're going to have the encoder output a distribution over possible z instead of a single representation. And then when we're running the decoder, we're going to sample from this distribution before decoding. The key point is that, remember when we said that we sort of wanted z to be distributed according to a Gaussian? Well, we can say, since the encoder is outputting a distribution, we can say that that distribution should be close to some prior distribution, for example, the unit Gaussian. And that's the key point, that the output of the encoder should be pretty close to a nice distribution over z, with independent features and features similarly scaled. Now, how do you formalize this? Here's a big loss function. Let's go into the details of this loss function and why it captures the intuition that we were just discussing on the previous slides. First, this term. This is just the term that we've been looking at all along. It is just the L2 norm, the squared L2 norm, of the difference between the input, x, and the output of the decoder, d of z. Only in this case, we had to sample z from the distribution e of x. That's just what the expected value means. It means the expected value if we're sampling z according to the distribution e of x. Now what's this term? This term is the KL divergence between the distribution e of x, the output of the encoder, remember it's a distribution, and the prior distribution p. KL it refers to the KL divergence, which is just a measure of distance between probability distributions. Formally, it's this. But you should think of it just as how far away is e of x from p. Now, formally, the KL divergence is a really cool thing. It's relevant a lot in many parts of machine learning. It's connected to entropy, mutual information. I'll let you explore it on your own. But just for the moment, just think of it as a way to measure distance between e of x, in this case, and p. Now, how do you actually build a VAE? Well, you're going to have neural networks. You're going to have an encoder. And this neural network is going to output two vectors, a mean and a variance vector. And your low-dimensional representation z, remember the output of the encoder is a distribution over z. So we're going to use that mean and variance to create a Gaussian distribution over Z. There are other ways to build this distribution, to parameterize it, but just assume it's Gaussian for the moment. And so you're using the mean and variance, the output of the encoder, to construct this Gaussian distribution. And then the decoder is just going to be a neural network that processes samples from the low-dimensional representation. You're also going to need a prior, which is the desired distribution over Z, for example, a unit Gaussian, as we've been discussing. Given all of these ingredients, the encoder, the decoder, and the prior, you can train the encoder and the decoder according to the loss function that we've already seen, which is just two terms. One of them is the Kale divergence between the encoder distribution and the prior distribution. The second term is just the squared L2 norm of the difference between your input and your output, your decoded output. Applied again to Z, sampled from your encoder distribution. So in summary, we've seen low-dimensional representations in many different forms, which are useful either in modeling low-dimensional representations within the brain or in working with high-dimensional data. And again, I'd like to caution, none of these low-dimensional representation algorithms is exactly how the brain does it. Just because there is a great algorithm that does some of the same things that the brain wants to do, doesn't mean that that's actually how the brain does it. But they can be sometimes useful models, and they can certainly be useful in working with high-dimensional neuroscience data or other kinds of data. We've seen some simple methods like PCA, NMF, ICA, and the algorithm to compress data, gzip, on your computer. And then we've seen deep learning methods, autoencoders, which are generally hourglass-shaped neural networks with a bottleneck layer between an encoder, which creates the low-dimensional representation, and a decoder, which tries to invert the encoder by generating high-dimensional data from low-dimensional representations. We've seen convolutional autoencoders, which use upsampling in the decoder to go backwards from a low-dimensional to a high-dimensional representation. We've seen sparse autoencoders, where instead of having a narrow bottleneck layer, you instead have a potentially wider bottleneck layer, but it's required to be sparse, have sparse activations. We've seen denoising autoencoders, where you add noise to the input before encoding, and that gives you a denoising algorithm as well as an autoencoder that is sensitive more to real features than to noise. And finally, we've seen variational autoencoders, where the encoder is actually outputting a probability distribution over your potential low-dimensional representations, and the decoder is sampling from that before doing the decoding. Enjoy playing around with these various algorithms for creating low-dimensional representation, and thank you.